Hello and welcome to my video on springs period. So it's similar to the pendulum period in the last video. The only thing that I did not mention in that video, so this is the formula for a pendulum. If you didn't watch it, I recommend watching that video as a lot of the skills are quite similar, basically the same. So this is the formula for a pendulum's period. And one thing I didn't mention was, by the way, period is measured in seconds. And everything should work out in terms of units. So this is what we have so far with length as meters and gravity as meters per second. So what you can know is if there's a fraction on the bottom of a fraction, well, it actually lets you flip. So the second squared can go on top. So the denominator of the denominator is actually truly just a numerator. So at this point, this is wonderful. Now our masses can cancel, so we're left with seconds squared. Now we can cancel our squared and our square root, and we're left with seconds. The beautiful thing is, if the units work out, you've probably done something right. If the units don't work out, you know for sure you've done something wrong. So here, the same thing works for a springs period. So we've got square root of mass, which is in kilograms, over the spring constant, which is newtons per meter. Okay, so let's just take another step forward before we take a step back, or take a step back before we take a step forward. So kilograms times meters, right? That's what we said before. We can flip that. But there's going to be another level after that, because newtons can be written as kilograms meters per second squared. So at the top we've got kilogram meters, and then we've got per second squared. So we're going to flip that one more time. We're going to get kilogram meters and then seconds squared, and then over kilogram meters. So at this point we can cancel out the kilograms with the kilograms on the bottom and meters on the bottom. So we're left with the square root of s squared, familiar, hopefully, because we can cancel those two parts out and we're left with seconds. So again, a lot of the skills are very similar in both sets. Springs are just using mass and the spring constant instead of length and gravity. So let's take a look at the first question, which is a very simple one, and using our formula here. All right, so let's look at the first question here. A 350 gram mass is attached to the end of a spring that is vertically suspended from the ceiling. The mass is pulled down and then let go. The spring begins to oscillate. So we've got our mass, so 0.350 kilograms. Determine the period of the spring's oscillation if the spring constant is 10.2 newtons per meter. So this is just noticing that, well, we have those two values and we're looking for t, so it's really, really straightforward. So we've got 2 times pi times the square root of the fraction of, and this is really the only thing that's quote-unquote difficult in this, is to notice that we have to be in kilograms, not in grams. But otherwise, everything is really straightforward. 1.163, how many sig digs do we have? 1.16, I believe. Yep, and that would be seconds. 3 sig digs. All right, nice and simple. Let's use the same sort of skills as in the last video. We're going to be doing opposite operators, opposite bed mass, in order to move things around. So to start with, we've got t equals 2 pi square root L over, oh, not L, see, did the last video, M over K. Let's take a look at this question. A mass is attached to the end of a known spring with a constant of 12 newtons per meter that is vertically suspended from the ceiling. The mass is displaced and the system begins to oscillate up and down with a period of 1.1 seconds. So we know the period, we know the spring constant, determine the mass. So we want to get mass by itself. So our first step is to divide by 2 pi on both sides, following again the same process as in the last video. If you want some more details, I recommend checking that one out. So those cancel here, and we're left with t over 2 pi on this side and the square root of m over k on this side. Now we can square both sides, and that will give us t squared over 4 pi squared equals m over k. This is fantastic, but we're not quite done yet. We need to do one more thing, which is to multiply by k on both sides in order to get rid of the k down here and have mass by itself. So t squared k over 4 pi squared equals m. Excuse me. So let's try this out. We've got a period of 1.1, and then we square that, times by the spring constant, which is 12, over 4 times pi squared, which is 0.3677. So 0.37 with sig digs. Okay, and that is our final answer. We often like to just put it into grams, but in this case there aren't enough sig digs to do so. So it is in kilograms in this case. All right, and this is again the most challenging question. It gets harder for each one of these questions in my videos. So this one is the hardest. So I recommend trying this out and seeing if you get to the same answer that I do in a moment. Pause the video, try it out, and then press play. All right, let's try this question out. A mass is hung vertically. Okay, so there's a ceiling, there's a spring attached to a spring, and then a mass is hung vertically. And it's stretched out, which means that because it's being hung, it's stretched out by 25 centimeters. Lifting the mass upwards 5 centimeters, then letting it drop, it begins to oscillate. What is the period of that oscillation? Well, this is a multi-step problem. That's what makes it a challenging question, and it might even be beyond the scope of this course because it uses a little bit more math skills in terms of system of equations. But I am going to show it to you because I think it is a wonderful example of a good combination question. So we've got the force of gravity pulling down, but we also have the force of the spring pulling up. At the beginning, it stretches it out. It is hung vertically, causing it to stretch out by 25 centimeters, i.e. the F net, I'm going to write that up here, the F net is MA, which is 0, which is FG minus FS. And so if you rearrange that, you get FG equals FS. Or another way to write that is MG equals, and then because we already have the direction of the force, we don't need to put a negative there. But anyways, we've got KX, because we already have that direction in the question. It's built in. Okay, so there it is. Now that doesn't really help us get to our final answer yet, but we can also take a look at the period, which is 2 pi over m square root m over k. So if we solve for m here, maybe we can substitute that in. So kx over, divide by g. So what's going to give us is m equals kx over g, which we can then substitute back in to the other equation. So t equals 2 pi square root, and instead of writing m, we're going to write kx over g. which is all over k. So rearranging this to look a little bit neater, it's going to be 2 pi square root kx over gk. And what do you notice? Hopefully k's cancel, so it's actually just 2 pi square root x over g. Okay, which is pretty crazy, but also wonderful. So we've got x, which is our stretch, how far it had to stretch down, so that was 0.25 meters, and then g, which is 9.81, assuming we're on the planet Earth, which is not always a fair assumption, but it's a good enough assumption for now. And let's go ahead and try this out. So 2 times pi times the square root of, and then 0.25 over 9.81, and we get 1.003, and we only have 3 sig digs, so 1.00 seconds. Alright, so like I said, this is a challenging one. It uses 2 parts at the same time, and you kind of have to just work at it until you figure it out. I would probably start, actually, now that I'm thinking about it a little bit more, I'd probably start at the period end, look here and go, oh, I don't have mass or the spring constant. How can I get those? Well, I know it's being stretched out, and I know that kx is going to give me my spring constant, and m is in the g, so maybe I can solve for one of them. You put it in, and you can't solve really, but you can sort of solve, and then things cancel. So that would be the process. I hope that this video helps you better understand springs and their periods and some of these challenging example questions. Hope this video helped, and good luck.